Hello everyone, welcome to the control system. This is part 2 of lecture 8 on stability analysis for linear system. In this section, we'll discuss root stability criterions. Okay? So consider the system represented in the form of transfer function below. This is a general case where a and b, this coefficient, are constants and m less than or equal to n. Okay, this is a generic form, and the stability of the closed loop system can be determined by location of the poles. It means that the root of the denominators. Okay, the root of the denominator is the location of the pole, and it is stable if all the poles lie on the left side of S-plane. So if all the poles lie on the left side, if you have S plane like this and it lie on this left hand side, then the system is stable. On the other hand, the system is unstable if at least one pole lies on the right hand side. So if there is only one pole lie on the right hand side of the S plane, and then the output will diverge for any input. Okay, the system is marginally stable if the poles on if there's a pole on the imaginary axis with all other pole on the left. Okay, it's just lie on the imaginary axis in this vertical axis, and the system is stable for some input and is unstable for others. We don't know, or maybe we know. Alright, let's have an example. For each closed loop transfer function t, Ts is a closed loop transfer function, and we can determine the stability of the system. For example, if the closed loop transfer function represented like this, you can solve the polynomial of the denominators, equate this to 0, you will find S. We'll be able to find S equal, in this case, S equal -1 and S equal -3. So it's lie on the left half planes. So it implies that the system is stable. Okay, and in this case, S lies on the imaginary axis, so it is imaginally stable system. So let's recap a little bit. Again, a control system is stable if and only if all closed loop pole, this closed loop pole, lie on the left half S-planes. So consider the closed loop system again, represent like this. There is a simple criterion known as root stability criterion. It enables us to determine the number of the closed loop pole that lie in the right half planes, S-planes, without having to factor the denominator of the polynomial. For example, in this case, it is a second order, so you can easily factorize this, okay, the denominator, and you find the pole. But if it's large, high order, it's very difficult to factorize it. And this root stability criterion will enable us to determine the number of the closed pole without having to factor the denominator polynomials. So the root stability criterion determines if any of the root lie outside the left half planes. Okay. However, it doesn't give actual pole locations. You can tell if it is stable or unstable. It doesn't give any information on the actual pole locations. Okay. So there are some procedure in root stability criterions. For example, not for example, the first step is to write polynomials where the coefficients are real quantities. So this a0, a1 to an are real quantities. And we assume that an is not 0. That is, all 0 roots have been removed. And then we have to check, okay, are there any coefficients that are equal to 0? For example, in this case, if you write like this, you can see that one coefficient will be equal to 0. So if you see it is represent like this, and then you can tell that not all roots lie on the right hand side, on the left hand side. Okay, and the second question is, are there any coefficients negative, or are any coefficients negative? So if and then at least one root is on the right hand side, it's an unstable system. Okay, so you don't want to have this. And next one is unstable system is possible with all positive coefficients. So if all of these are positive, uh, the it can be unstable. The system can be unstable. So in that case, you need to use root stability criterions. Okay. Again, on step 2, we need to check the coefficients. If this, if the 0 coefficient exists, then not all roots lie on the left hand side. And if you have a negative coefficient, it is unstable system. And last but not least is unstable system is possible with all positive coefficients. So in that case, you need to use oh no, you need to use root stability criterion. Okay. Next, we're gonna learn how to form the root array. So this is the polynomials of the denominators, and then we have to form the root array. So this is the largest order, so you need to write this into this column vectors Sn minus 1 until S0, and the coefficients, so A0, A2, A4, A6, and so on. This is evens, and this is odd, 1, 3, 5, 7. Okay. Once you have these two rows, you need to do some calculation in order to obtain the third row, the 4 rows, and so on. For example, B1 is equal to minus 1 over A1, 1 over A1, so you have a minus sign. So this row here, minus A1, and then the determinant of this one. I mean, A0, A2, 1, 3. Okay, and then you need to do to calculate the determinant to obtain B1, the coefficient B1, and also B2. So B2 the same, or minus 1 over A1, but the denominator is the determinant is different. So A1, A0, A1, and this is A4, A5. Okay. C1, yeah, you need to change this coefficient, minus B1 in this case. This is B1, and then doing the calculation of this determinant. C2, the same procedures. Okay, also D1, D2 if you want. And then next you need to count the number of change in sign in the first column. So this column, you need to count the number of changes in sign in the first column. So the number of change in signs in the first column is equal to the number of root on the right hand side. Okay. So if there is no sign change, then the system is stable. And if there is sign changes, then the system is unstable. Thank you for watching this video.